America's most dangerous volcano is shaking like never before. And the strange part is that almost none of the people living beneath it could feel what was happening. Deep underneath one of the most beautiful mountains in the United States, thousands of tiny earthquakes suddenly began breaking through the silence. The shaking started on July 8, 2025. At the busiest point, the earthquake rate climbed above 30 events per hour. Then the swarm continued, day after day, week after week. More than 100,000 people live in towns built right on top of mud and rock left behind from the last time this volcano let loose. By the time the activity finally faded on August 25th, more than 1,350 earthquakes had been located, along with thousands of smaller events too tiny to locate individually. It was the largest earthquake swarm ever recorded at Mount Rainier, and that immediately raises a terrifying question. What happens when America's most dangerous volcano suddenly starts shaking like never before? Is magma moving upward? Is pressure building underneath the summit? Is this volcano about to erupt? Could this be the beginning of an eruption, or is something else happening deep inside the mountain? Because Mount Rainier has a secret that most people never think about. Its greatest danger isn't necessarily lava, ash, or even an eruption. The danger is what happens when enormous amounts of ice, water, and weakened volcanic rock exist on the same mountain above heavily populated valleys. A sudden collapse could transform that peaceful mountain into the source of a massive lahar, a fast-moving mixture of water, mud, rocks, and volcanic debris. And some of those valleys below Rainier are not empty wilderness. They contain communities, schools, highways, businesses, and homes. Tens of thousands of people live and work in areas that could be affected by a major lahar. So the earthquake swarm of 2025 wasn't just another strange geological event. It was a rare opportunity to watch one of America's most closely monitored volcanoes reveal what is happening beneath its surface. And what scientists discovered was both reassuring and unsettling. There was no evidence that an eruption was imminent, and Mount Rainier remained at the normal alert level. The earthquake activity eventually returned to typical background levels, but the mountain had still sent an unmistakable message. It is active, it is moving, and there is an enormous amount happening beneath that snow-covered summit that we cannot see with our own eyes. Today, we're going to follow that story from the first earthquake to the scientific investigation, and then deeper into the real hazard that makes Mount Rainier so dangerous. Because once you understand what is underneath this mountain, you may never look at that beautiful white summit the same way again. Before we go any further, if you enjoy deep dives into earthquakes, volcanoes, extreme weather, and the hidden forces changing our planet, make sure you're subscribed. Because some of the most important stories happening on Earth don't begin with a giant explosion. Sometimes they begin with something much smaller, a vibration, a crack, a shift, a signal appearing on a scientist's screen. And on July 8th, 2025, one of those signals began appearing again and again beneath Mount Rainier. Let's start there. From almost every angle, Mount Rainier looks like the definition of a peaceful mountain. Its summit rises more than 14,000 feet above Washington state. Snow covers the upper slopes, glaciers wrap around the mountain, and forests spread outward from its lower elevations. On clear days, the enormous white peak dominates the landscape. People photograph it, hikers climb it, tourists drive toward it, and artists paint it. And for millions of people in the Pacific Northwest, Rainier is simply part of the background. One of those landmarks people eventually stop noticing because it has always been there. But geologically, Mount Rainier is anything but quiet. It is an active volcano belonging to the Cascade Volcanic Arc, and it has erupted many times during its geological history. That doesn't mean an eruption is happening now, or that one is about to happen. And it doesn't mean every earthquake beneath the mountain is an eruption warning. But it does mean the mountain contains an active volcanic system, and that system is continuously monitored. The USGS and the Pacific Northwest Seismic Network maintain instruments around the mountain to detect earthquakes and other changes. That monitoring is incredibly important because volcanoes don't always announce their behavior with dramatic explosions. Sometimes they whisper. A tiny earthquake, a change in gas chemistry, or ground movement too small for anyone standing there to notice. And sometimes several of these signals appear together. That's why scientists don't simply look at one earthquake and decide whether a volcano is dangerous. They look for patterns. They compare current activity with years of previous measurements and watch how the mountain behaves over time. And this is exactly what made the 2025 Rainier swarm so unusual. The scientists weren't watching an unmonitored mountain. They had decades of data telling them what normal Rainier activity looked like. So when the earthquake rate suddenly increased, they immediately had something to compare it against. And the comparison was extraordinary. Rainier had never produced a swarm like this in the modern instrumental record. But before we get into the swarm itself, we need to understand something even more important. Why is Mount Rainier considered such a serious volcanic threat in the first place? The answer begins with ice. A lot of ice. Mount Rainier has 25 major glaciers. That makes its relationship with ice unusually important when scientists study its hazards. Imagine standing at the base of the mountain and looking toward the summit. What you see is not just volcanic rock. You're looking at a gigantic natural reservoir of frozen water. Snow accumulates, gets compressed, and becomes ice, which slowly moves downhill through the mountain's glacier systems. For most of the year, this looks completely ordinary, but during an eruption, rapid melting could dramatically increase the amount of water available to mix with loose volcanic material. And even without an eruption, Rainier has another geological problem. Parts of the mountain's rock have been weakened by hydrothermal alteration. This sounds complicated, but the basic idea is surprisingly easy to understand. Deep inside an active volcano, heat interacts with groundwater, and that hot water and steam move through cracks in the rock. Over enormous periods of time, the hot fluids chemically alter the minerals, and the rock changes. Some of it becomes much weaker. Instead of behaving like a solid block of strong volcanic stone, altered material can become clay-rich and unstable. USGS studies have documented extensive hydrothermal alteration at Rainier over its geological history. Now imagine the mountain as a giant structure. Enormous quantities of snow and ice at the top, steep volcanic slopes underneath, rock weakened by hot fluids inside those slopes, and valleys below that carry water away from the summit. That combination is the foundation of Rainier's biggest hazard, a lahar. The word lahar may not sound especially frightening, but imagine a river that isn't made of clear water. Imagine it is made of water mixed with mud, volcanic ash, gravel, rocks, trees, and enormous boulders. Now imagine that mixture moving downhill with tremendous force. That is the basic idea behind a lahar. USGS identifies lahars, also called volcanic mud flows or debris flows, as the greatest potential volcanic hazard at Mount Rainier. And here's the part that makes Rainier unusual. A lahar does not always require a major eruption. A large mass of weak, water-saturated rock can collapse from the volcano slopes. Once that material begins moving downhill, it can pick up more water and sediment, and the flow grows and accelerates. It follows valleys, and eventually it can travel far beyond the mountain itself. This is not simply a theoretical possibility. Rainier has produced enormous lahars in the past. One of the best-known examples is the electron mud flow, which occurred roughly 500 years ago. USGS describes the electron event as beginning with an avalanche of hydrothermally altered rock high on Rainier's west flank. Its onset cannot be clearly tied to volcanic activity, and the weakened water-saturated material helped transform the collapse into a major mud flow. That history matters because it tells scientists something extremely important. The mountain does not need to erupt dramatically for dangerous material to move downhill. The ingredients can already exist: weak rock, water, gravity, and a steep mountain. That is why scientists continue to monitor Rainier, even when there is no sign of an eruption. The mountain can be quiet volcanically and still represent a significant debris flow hazard. And that brings us back to 2025, because something inside Rainier suddenly became much noisier. It was early morning on July 8th, 2025. At 1:29 a.m. Pacific time, the earthquake swarm began. At first, individual earthquakes may not sound particularly dramatic. Most were tiny, and many were far too small for people at the surface to feel. But the instruments could detect them, and then another earthquake arrived, then another, then another. The rate increased. At one point, more than 30 earthquakes were occurring per hour. That's when scientists knew they weren't looking at ordinary background activity, they were looking at a swarm. An earthquake swarm is different from the kind of earthquake sequence most people imagine. Normally, when we hear about an earthquake, we think about one large main shock followed by aftershocks. But a swarm can behave differently. There may be no single dominant earthquake. Instead, many small earthquakes occur within a relatively compact area over a period of time. At Rainier, the activity was concentrated beneath the volcano, and the number of events kept growing. USGS reported that within the first days, hundreds of earthquakes had already been located, with even more tiny events occurring beneath the detection threshold for individual location. Then something became obvious. This wasn't going to be a one-hour event. The swarm continued. The earthquake rate eventually declined from its initial peak, but the activity persisted. Scientists continued tracking it. They mapped the earthquakes, measured their magnitudes, and examined their depths. And they compared the pattern with previous Rainier earthquake swarms. The deeper they looked, the more unusual the event became, because this wasn't simply a swarm. It was the largest earthquake swarm ever recorded at Mount Rainier, and that immediately created a question nobody could ignore. Why? When people hear that a volcano is suddenly producing earthquakes, the first thought is obvious: magma. Deep underground, molten rock is moving, pressure is building, something is pushing upward. And sometimes that really is what earthquakes around volcanoes can indicate, but scientists can't assume that, because volcanic earthquakes can have multiple causes. One possibility is magma movement. Another involves fluids. Volcanoes contain enormous amounts of fluid. Water moves through cracks, steam moves through fractures, gas moves through openings, pressure changes, and rock responds. And all of that can produce earthquakes. So scientists needed to determine which process was responsible for the 2025 swarm, and this is where the monitoring system became incredibly important. Because if magma were rising significantly toward the surface, scientists would look for additional evidence. Changes in the shape of the volcano, volcanic gases, earthquake patterns, and surface conditions. They could compare everything with previous eruptions and unrest. One signal by itself wouldn't be enough, but several independent signals pointing in the same direction could tell a much clearer story. And scientists started checking. One of the most important things scientists watch at a volcano is deformation. The idea is simple. If magma enters a shallow part of the volcano, it can sometimes push the surrounding rock outward and the mountain can swell. The ground can move by an amount too small for people to notice, but GPS instruments can detect it. So scientists looked for evidence that Rainier was deforming in a way consistent with magma movement. They also looked at the gases escaping from the volcanic system, because volcanoes release gases that can provide clues about what is happening underground. Changes in gas chemistry can sometimes indicate changes in the movement of magma or heat. During the 2025 swarm, scientists carried out gas monitoring to help understand the situation, and USGS reported that the gas observations did not indicate a significant change, suggesting an imminent eruption. That was an important clue. Then there was the seismic pattern itself. Scientists examined where the earthquakes were happening and how their activity changed over time, and the overall picture began to point away from a major magmatic intrusion. Instead, the evidence was increasingly consistent with processes involving the volcano's hydrothermal system. In other words, the mountain was shaking, but the shaking did not mean that a giant blob of magma was necessarily racing toward the surface. And this distinction is critical because a huge earthquake swarm can look terrifying on a graph. Thousands of little dots, numbers rising rapidly. But numbers alone don't tell you what caused them. You need context, geology, chemistry, deformation measurements, and you need to know how the volcano behaves normally. That is exactly what scientists were doing. Deep inside, Rainier is a complicated hydrothermal system. Think of it as a giant network of cracks and pathways through which hot fluids can travel. Heat from the volcanic system warms water underground. The water moves, and pressure changes. The fluids encounter fractures. Some pathways become more open, others become sealed. And when fluids move through fractured rock, they can alter the way stress is distributed, which can cause small sections of rock to slip. When they slip, they produce earthquakes. It is a little like a giant underground plumbing system. Imagine water moving through a maze of pipes, except those pipes are cracks inside solid rock. Pressure changes, the cracks adjust, and some areas suddenly move a tiny amount, releasing energy that travels outward as seismic waves. At the surface, you might feel nothing, but deep underground, the mountain has just moved, again and again and again. That is one reason hydrothermal systems can generate earthquake swarms. And Rainier is particularly suited to this kind of activity because it has a long-lived volcanic heat source and extensive hydrothermal alteration. The same hot water processes that can weaken rock over geological time can also influence seismic activity that creates an unusual connection. The earthquake swarm and the lahar hazard are not necessarily the same event, but both involve the complicated interaction between heat, water, rock, and pressure inside the mountain. And that is why scientists care so much about understanding the hydrothermal system. It isn't just an academic exercise. It helps them understand the volcano's structure and interpret future earthquake swarms. And it helps them understand why some areas of the mountain are more mechanically unstable than others. Eventually, the question became much clearer. Was Mount Rainier about to erupt? The available evidence said no. The earthquake swarm was extraordinary, but there was no corresponding set of signals indicating that an eruption was imminent. The volcano remained at green, or normal, and by August 25th, the earthquake activity had returned to typical background levels. That conclusion may sound anticlimactic. After all, we just talked about more than 1,000 earthquakes beneath one of America's most dangerous volcanoes. But this is where science becomes more interesting than a scary headline. The dramatic explanation isn't always the correct explanation. The mountain was not necessarily preparing to explode. It was showing scientists how active its underground system could become. And because the monitoring network was already there, scientists were able to watch that process almost as it unfolded. But there was still a bigger story because the end of the earthquake swarm did not erase Rainier's long-term hazard. The mountain was still covered in ice, the hydrothermally altered rock was still there, and the communities below were still there. A glacier can look completely stable. From a distance, it appears frozen, motionless, permanent. But glaciers move. They flow slowly downhill under their own weight, respond to temperature, and gain and lose mass. And on a volcanic mountain, that movement interacts with everything underneath. Rainier's glaciers are an enormous part of the mountain's hazard system. During an eruption, rapidly melted ice and snow could provide huge amounts of water that mixes with loose volcanic material and generates lahars. But even without an eruption, glacier-fed debris flows occur at Rainier. USGS notes that torrential rain, glacial outbursts, and water saturation of steep, debris-covered slopes can produce debris flows around the mountain with surprising frequency. This is important because it shows the difference between a volcanic hazard and an eruption. A volcano can have hazards even when it isn't erupting. Rainier is a perfect example. The mountain can experience heavy rainfall, snow can melt, glacial water can surge, and loose debris can become saturated. A slope can fail, and suddenly material begins moving. That doesn't mean a catastrophic lahar is happening every time it rains. It means the mountain's physical system is capable of producing debris flows through multiple pathways, and scientists need to understand all of them. One of the most important parts of the Rainier story is the altered rock. Imagine taking a strong brick and soaking it in harsh chemicals for an extremely long period. It might not remain as strong as it was originally. Now imagine that process happening naturally inside a mountain for thousands of years. Hot water and steam circulate through volcanic rock, minerals change, and clay-rich materials form. The rock loses some of its original strength. Now place that weakened material on a steep slope. Gravity is constantly pulling on it, water can enter it, and ice can sit above it. And the whole system becomes more complicated. This is one reason scientists study hydrothermal alteration so closely. It can influence the stability of volcanic slopes. At Rainier, the electron mudflow provides a powerful example. An enormous mass of hydrothermally altered rock collapsed from the volcano's west side. The material was water-saturated and clay-rich, and once the collapse began, it transformed into a massive debris flow that traveled far from the mountain. The event happened centuries ago, but the geological lesson remains. Rainier contains areas where volcanic rock has been weakened by its own internal heat and water. That doesn't mean those areas are about to collapse. Scientists cannot predict a specific collapse simply by knowing that altered rock exists. But it does mean the mountain has a structural vulnerability that makes its hazards different from those of many other volcanoes, and that brings us to the people below. Imagine living in a town where the mountain is visible on the horizon. You wake up, go to work, take your children to school, drive down the highway, buy groceries, come home. Nothing about the day feels dangerous. The mountain looks beautiful. Maybe there's snow on the summit, maybe clouds are moving across the slopes. But underneath the ordinary surface of daily life is a geological history stretching back thousands of years. Some of the valleys below Rainier contain deposits from ancient lahars, evidence that massive flows have traveled through these landscapes before. And today, people live on those same landscapes. That creates one of the biggest challenges in natural hazard planning. The danger is invisible. You cannot look at a neighborhood and immediately know that a prehistoric mudflow once passed through that valley. You need geological maps, hazard models, historical evidence, and monitoring systems. USGS hazard maps show potential lahar pathways and arrival time estimates for communities and valleys around Rainier. These maps aren't predictions. They don't say a lahar will happen tomorrow, but show where a future event could potentially travel based on the mountain's geology and topography. And those maps are extremely important for emergency planning, because when a lahar begins, the people downstream need to know their route beforehand, not figure it out in the moment. A hurricane can often be tracked for days, a major winter storm can be forecast well ahead of time, and even some volcanic eruptions provide warning signs over weeks or months. But a lahar caused by a sudden collapse can be different. The collapse may happen quickly, and the resulting flow can accelerate downhill. That means the warning system has to detect the event as it happens, and that is exactly what the Rainier Lahar Detection Network is designed to do. USGS describes lahar detection systems that monitor for the distinctive ground vibrations produced by moving debris and rapidly notify emergency officials when a lahar is detected. Think about what that means. A sensor sits quietly in a valley, and most days nothing happens. Cars pass, rain falls, rivers move, people go about their lives. Then one day, if a large debris flow enters the drainage, the ground begins vibrating in a distinctive way. The sensor detects it, and the signal is transmitted. Emergency officials receive the information, warnings can be issued, and people can move toward higher ground. The technology itself may be invisible to almost everyone, but in a disaster, those invisible systems can become the difference between warning and surprise. A warning system is only useful if people know what to do, which is why in 2024 more than 45,000 students, teachers, and staff participated in what USGS described as the world's largest lahar evacuation drill, turning uncertainty into automatic, practiced response. The 2025 swarm didn't create the pre-existing lahar hazard, but it gave scientists an extraordinary natural experiment into the mountain's active internal system to compare against any future swarm. And it reinforced the key lesson that earthquake count alone never equals danger level, since alert levels depend on the entire pattern of evidence, not just the number of shakes. Rainier's geological record already carries this warning through centuries-old lahar deposits like the electron mud flow, and USGS guidance is clear on response. A landslide of saturated debris can rapidly transform into a fast-moving flow confined to valley drainages. So the only safe move is to get out of the flow path and reach higher ground immediately. Around the volcano, seismometers, GPS stations, gas instruments, cameras, and lahar sensors feed a continuous stream of data that lets scientists tell a boring, normal day apart from a genuine emerging threat, resisting the urge to panic or issue false alarms over any single unusual signal. In the end, Rainier's danger isn't that it erupts constantly. USGS rates its threat potential as very high, specifically because of the combination of a huge glacier system, hydrothermally weakened rock, steep slopes, a history of major debris flows, and densely populated valleys downstream, and the 2025 swarm, the largest ever recorded there, running from July 8 to August 25, with no evidence of an imminent eruption, was a reminder that the goal of monitoring is preparedness, not fear. Since the mountain remains an active, unpredictable system, scientists continue watching closely as of 2026. From the surface, nothing changed. Cars still drove through Washington, hikers still climbed the trails, and the snow-covered summit looked exactly the same. But beneath that peaceful postcard image, heat, water, and fractured rock kept moving, a reminder that the mountain is still speaking in the quiet language of seismic waves, and that the next warning may begin, not with an explosion, but with one tiny signal scientists will be watching for. So subscribe to Nemora Proof to be there when it happens.